Hi, I'm Simpson Garfinkel, and this is my AAFS presentation on Keeping Forensic Tools Sharp, a case study of updating bulk extractor from version 1.6 to 2.0. In this talk, we're going to talk about why digital forensics tools require continual updating. I'm going to give bulk extractor as a case study, and then I'm briefly going to discuss what this means for open source digital forensics. So digital forensics tools require constant maintenance, and for 4 reasons. The first is operating system creep, the second is language creep, the third is forensic science creep, and the fourth is the operations and maintenance tail. Operating system creep simply means that the operating systems that we're analyzing change over time. But the operating systems that we're using to do the analysis also change over time. Some forensics examiners use Linux, others use Windows, others use Mac OS. And those operating systems, the ones we use for analysis, have to be constantly upgraded because of bugs and security vulnerabilities. And unfortunately, new versions of the operating systems may not run old versions of forensic apps, and new versions of apps may not run on old versions of the operating systems. There's also the issue of language creep, and by language I mean the computer language in which the digital forensics tool is written. Now this is mostly a concern for open source software because open source software is distributed in source code form. It turns out that today's operating systems are much better at preserving compatibility at the binary level because of the application binary interface than at the source code level. And a good example of this is Java. If you have Java source code from the early 2000s, it pretty much won't compile on a modern Java compiler. But if you have a compiled Java program in the form of bytecode from the early 2000s, it will frequently run on a modern JVM. And if you have bytecode and a JVM from the early 2000s, the combination will almost always run on a modern OS, because the old JVM is using an ABI, an application binary interface, that is very stable. There's also creep with digital forensics itself. Digital forensics keeps getting better. We keep learning more about today's computer systems. But at the same time, we're struggling to keep up. There's new systems coming out, new compression algorithms, new memory structures. And so it's a constant struggle in digital forensics to keep up. The field keeps moving. Finally, there's the issue with the operations and maintenance tail. All software needs to be maintained, and digital forensics software is no different. We discover bugs in the software, and the environment as a whole updates. There's new hash algorithms of particular interest in digital forensics. So now I'm going to talk about bulk extractor, which is a digital forensics tool that I developed in the early 2000s, and I've recently been working to update it from version 1.6 to version 2.0. Now, bulk extractor is a command line digital forensics tool written in C++ with about 59,000 lines of code, and it was originally written in the 1998 C++ standard. It also has a Java-based graphical user interface, and both are compiled using the Autoconf toolchain. It runs on Mac OS, Linux, and Windows, and it's a high-performance multi-threaded carving and identity extraction tool. You can download it from GitHub. There were a lot of reasons to update bulk extractor. The first was maintenance cost. Every time a new release of an operating system came out, I needed to update the tool so that it would compile on the new operating system. Also, bulk extractor used some out-of-date versions of Python, and it actually got banned from a Linux release because it was still using Python version 2. There have also been changes in the CPU I/O memory trade-off. The speed and the relative speeds of CPU, I/O, and memory has changed over the past 10 years. And pretty much CPUs are faster, memory is faster, but networks didn't get as fast as CPUs and memory did. It turns out that large parts of bulk extractor were single-threaded, and they really became bottlenecks. They've had to be re-architected so that they could be multi-threaded. Of course, the most important reason to update a tool is correctness. It's important for the tool to be right. Unfortunately, most computer programs that are written have the luxury of being able to follow formal specifications or informal specifications. But most of digital forensics is based on reverse engineering. We don't have specifications for the tools and the programs that we're trying to understand. Many parts of digital forensics tools crash or print warnings when they run, and the same was true of bulk extractor. In fact, there's a test disk, and when I ran it, it was generating exceptions saying that there was some memory overruns on some internal software. Now, this wasn't causing a crash, but it was a correctness issue, and I suspected that there were other correctness issues. So I put together a formal update plan with objectives, and they're listed here, and I'm going to go through them. The first objective was to make the program easier to compile and maintain. So the main way I accomplished this objective was by moving to the C++ 17 standard. Now, originally I was moving to the 14 standard, but the project took too long. And for those of you who do C++, the standards have moved a lot of things that had to be manually configured before into the standard, which means there are fewer if-defs and fewer code that has to figure out if it's running on POSIX or Windows, for example. But just moving to the standard isn't enough. You have to be sure that the tool chain you're using to compile the program actually supports the full standard. And that's why I'm using C++ 17, even though C++ 20 is now out. The support for C++ 20 is just not as good. So bulk extractor 1.6 was tested the way a lot of digital forensics tools are tested. I basically ran the program and looked at the results. But with 2.0, we've introduced a lot of systematic testing. Individual unit tests for lines of code, end-to-end regression tests, and it's all automated as part of the build process. It happens both on the developer's computer and it happens on GitHub. And I'm using a C++ framework, and I'm also using instrumentation in the compiler to catch things like address overruns and to catch invalid sharing between C++ threads. Here's an example of a unit test. It is the base64 identification and extraction section. It has a base64 piece of code that is in the test program. We then run the function inside bulk extractor that's supposed to recognize the existence of base64, and we check to make sure that we get the correct result. We then decode it, and we check to make sure that we get the correct result. And this test program is distributed with bulk extractor. The self-test can be run on any machine that it's installed on, and it also gets run on GitHub when the code gets committed. Now, the end-to-end tests actually get instrumented with the same framework, and the way I did this was no longer do I have the main bulk extractor function being called main. Now it's called bulk extractor main, and it is then called with the command line arguments from the test programs. This makes it much faster, and this also allows me to test all of the command line arguments, and I can test them from within C rather than having to test them using Bash or Python. So I've mentioned a few times that this is on GitHub. I also wanted to make it easier for others to contribute code. The bulk extractor uses Git modules for increased separation between components, and I actually use GitHub Actions, which are programs that run every time there's a commit, to perform the continuous integration tests on every time there's a commit or a pull request. So this sort of system engineering is missing from a lot of open source forensic tools. A lot of them are done as one-off student projects or one-off tests for a particular client. With Bulk Extractor 1.0 and 2.0, we've really made an effort to use a high quality of software engineering. Here's an example from GitHub where each commit, the ones with the check marks are the ones where the self-test passed, and the ones with the red X's are ones where the test didn't pass. And what this shows is that the Bulk Extractor test program is not running properly on FreeBSD, and that's something that would have to be fixed prior to the release. Over the past 10 years, there's been a lot of interest in code coverage tools, and you can put a badge on an open source tool showing the percentage of the code that is actually covered with unit tests. And in this Bulk Extractor module, we're covered 60% of the code with the unit tests. That gets displayed on another website, which is called Autoconf, which integrates with the software development tools. Autoconf allows me to see the particular functions and files in Bulk Extractor and to see which ones need better code coverage and which ones are well covered. And in fact, I can even see line by line which lines are covered with code coverage, with unit tests, and which ones are not covered. Now, this kind of instrumentation has been in the GCC compiler since the 1980s, but it hasn't been widely used in the open source development community until recent years, and it isn't widely used in digital forensics at all, at least not to the best of my knowledge. So Bulk Extractor also had a lot of experimental code in it, which we removed. It was there for producing academic papers largely. And it also had a complex code base, and we spent 2 or 3 years refactoring the code base to make it easier to understand and to make it more reliable. For the end users, one of their primary concerns is runtime. So we wanted to decrease all of the runtimes on the same hardware. We wanted to make it faster to develop. We wanted to make the program use the CPU more efficiently. We wanted to make it use all the cores. And we wanted to add instrumentation internally so that we could understand what was taking up all the time and optimize it. So in this part of my talk, I'm going to see how well we did. I'm going to compare Bulk Extractor version 1 and version 2. So certainly Bulk Extractor 2 is a lot smaller than Bulk Extractor 1. It has far fewer C++ files. It has about 13,000 fewer lines of code, and the Java GUI has been moved into another Git project. The program runs the configure script much faster, and it compiles in about the same amount of time. I'm not going to show runtime performance because that's still under development. What's really exciting to me is that the program is finding more things on the old data targets. The Bulk Extractor has a carver in it, and it is finding dramatically more JPEGs than previously. It has a program that looks for Windows executables, and it's finding many more of those, and it's finding more zip files and zip file components. And this is because of the focus on correctness and the focus on unit testing. There were just a lot of things that were being missed by the old program, and I didn't know that. So what does this mean for digital forensics tools? Well, certainly when we bring out new releases, we need to validate them against previous releases in a systematic manner. I believe that the results need to be published in a machine-readable form. So one of the things that Bulk Extractor does is that all the outputs are stored in an XML format, so I can actually have tools that compare what version 1 and version 2 found and produce difference reports. And I can clearly document the new data that's recovered from legacy data sets. I can document the data that's recovered from new data sets that the previous version would miss, and I can also document overcollection that has been eliminated. So we need to set expectations with digital forensics tools. Complete rewrites are very expensive and slow. It took 10 years to get from Ethereal to a Wireshark. Volatility, it's been years in a rewrite from version 2 to version 3, and the individual rewrites, new versions come out pretty slow. It's unclear how we can make similar measurements with proprietary tools, but moving forward, I think that digital forensics as a profession, we need to pay a lot more attention to keeping our tools up to date and to clearly validating and documenting what changes between releases. Thank you very much.